you have an error somewhere. A negative number indicates that it's exothermic. A negative delta H or a negative, yeah, it's exothermic. It depends upon what the question is, but sign errors are the biggest problem in thermodynamic problems. I think that if you said, were you using Q equals mass times delta T? Is that the question is that the formula you were using? I don't know what the problem was. If you're using Q equals mass times delta T, and you end up with a negative number, that's an exothermic reaction, and I would check to make sure you put T final minus T initial. Because if you have those two numbers switched, you'll alter the sign.
I think this one was for a bomb calorimeter.
Bomb calorimeter. It still doesn't matter. Even for a bomb calorimeter, if Q is negative, that's exothermic. In fact, almost every reaction in a bomb calorimeter is going to be exothermic because they just generally are. They're usually combustion reactions. But we can look at the problem later if you want.
All right, no problem.
Okay.
Thank you.
Okay, not everyone is here, but I did want to do a few things. I wanted to go over a few things. Okay, another. Homework due dates. I have changed all of the homework 9 due dates to Thursday, the 10th. So you should, I would like them done. Thursday is our last class. It's the last time we'll get together. I'll tell you more about the final then. And you can ask questions at that point. So I've set all of the chapter 9 homeworks due for Thursday. I extended those. A number of you have asked me about the review quizzes. And I've taken all of the review quizzes from Newton and I have changed the final due dates on those to December 15th, which is next Tuesday, which is, I think, your reading day. Those of you who have not done them, obviously you can do them. A number of you have asked if I could open them again for you to try again to get practice. Here's my problem. When I go into those quizzes on my system, it says that you have unlimited attempts. There's 2 choices there in the settings. One is limited attempts, the other is unlimited. They are set according to my system as unlimited attempts. I can't change it any other way. There's no option for me to open it up for you to take it again or anything like that. So I have extended the due dates. That may open them up for you to try them again. I don't know. There's no setting that I can change, is all I'm telling you. But what I have done is I have taken all of those quizzes and I've extended the date to December 15th. So you can certainly go in and try doing them. Your reading day is the 15th, which is next Tuesday. Here is the problem, excuse me, here's the problem with Zoom versus Microsoft Teams. And the rest of the department, I think, uses Microsoft Teams. Microsoft Teams is set up where you can make a phone call. So you can essentially call in to me if you want help. Zoom, I have to open the meeting. And so it's set up a little bit differently. I will be essentially available all day. That doesn't mean I'll have my camera on all day, but I will be available all day. I will probably open the meeting and leave it open. If I'm not here, if you try to enter the meeting and I'm not actively sitting and in front of my computer and I don't see you, send me an email. I'll obviously see it on my phone and I can let you in. But I will essentially be, or you can send me a request ahead of time and say, can you be available at this particular time? You know, at 10 o'clock in the morning or 4 o'clock in the afternoon. I will essentially be available for you pretty much that whole day. So if you have questions, please feel free to contact me and we can go over any questions that you have. The last thing I want to say, and unfortunately not everybody is here, but I was asked by a student about dropping the course. Several of you have fallen significantly behind in your labs. Most of you have done most of them, and I will drop the lowest. So if you've skipped one or missed one, obviously I can drop that. But several of you have fallen significantly behind in labs, to the point that I don't think it's realistic that you can make up all of those labs. And those zeros for those labs are having a considerable impact on your grades. You can technically pass with I think a 65 or in the 60 range, you can technically pass the class. It is not recommended that you go on to Chemistry 2 unless you have at least a C in the class. So while you can pass, that credit may not be transferable to another school, and you probably will not be allowed to go on to Chemistry 2. If you are below the 60 range and you feel like it's largely because of work that you've missed and that you really can't get caught up, the drop date has been extended. You won't get any money back, but you can drop the class. The deadline for that is the last day of classes for the semester, which is next Monday. All the Monday classes, because of the way the semester started, the Monday classes go through to next Monday, which I believe is the 14th. So you have until Monday the 14th. If you are in that category that you know you're not going to pass and you know that you're not going to be able to get caught up, you can drop the class so that you don't have an F on your transcript, but you need to contact RVCC as soon as possible to do that. Some of you have asked if I'm teaching next semester. I am told that I am supposed to be teaching next semester. I was told that they have requested that I be put on the schedule to teach Chem 2 next semester. They're waiting for the dean to do that. And I believe my understanding is that the reason there is a holdup is that the classes that are available are not filled. And so the department has asked the dean to put my name on the schedule, but as of this morning, it was not. And I believe that that is the holdup, that the classes that are already available are not full. So any other questions, or do you have any questions about what we've done or what I've said so far?
Yeah, I have a question regarding the review quizzes. So they say 0% on Canvas. Is that they don't affect our grade?
That's because they're not calculated in your grade. They're extra credit. I look at your grades, I look at what you've done, and then I add it as an extra credit in whatever amount of extra credit I'm going to add. So yes, it says 0% on Canvas. It should say 0% for concept checks as well, because they are not factored into your grade.
Okay. All right, cool. Thank you.
Okay, any other questions?
I didn't know about the review quizzes, but can I still, as long as I get them in by the end of the semester, is that fine? Like, will they still go for extra credit?
Yes, they will.
Okay, thank you.
We're talking about the EC K Newton quizzes, right?
Yes.
Okay.
Anything else?
Do we
Professor,
have? Oh, you can go.
Okay. Does the points go towards the final or the overall grade?
It goes to the overall grade.
All right. Thank you.
Was this today our last quiz?
Today is your last quiz. Today's your last class that we're actually doing new material, actually. So,
Last question.
Yeah.
For the quiz, I kind of took it before the class though. So,
today's quiz,
yeah,
I didn't think it was open, but okay. Oh yeah, I guess maybe I did. Okay, that's fine. It is what it is.
yeah, but I wanted to ask a question for the last one.
The
I
last
know
one,
everybody
what?
got, oh, never mind. After class.
Okay.
Yeah,
Yeah.
sorry.
All right. Okay. Okay, so let me, I think this is where we left off. Tell me if this looks familiar. I think we did
Yeah.
standard states. Yes. Okay.
We talked for like 5 minutes on it.
Okay. So standard states are just a reference point. The energy changes that occur in either a process or chemical reaction will vary depending upon the temperature and pressure under which that reaction or phase change or whatever it is under whatever situation, under the temperature conditions, pressure conditions, etc. They vary. So you have to have a reference point. And this is the reference point. The standard states is the reference point. Okay, so there are, this is what we call special enthalpies. I don't want you to panic when you see something that says delta H sub whatever. That little subscript is basically telling you what type of enthalpy you're talking about. So for example, delta H sub C, often you'll see that as written out as COMB for combustion. That's the enthalpy of combustion. All that is telling you is what that reaction is. It's telling you that it is a combustion reaction. That immediately should tell you we're talking about taking that substance, combining it with oxygen, producing carbon dioxide and water. That's what a combustion reaction is. You can have combustion reactions of metals. So for example, the combustion of magnesium would be magnesium metal plus oxygen forming magnesium oxide. So not the products carbon dioxide and water are always true for organic compounds, but you can have combustion of other substances as well. But it always should mean combining with oxygen. That's what an enthalpy of combustion is. The second type of special enthalpy is an enthalpy of formation. Oh, before I do enthalpy of formation, I should say, point out that the enthalpy change is when 1 mole of the substance burns under standard conditions. And I'm going to show you a table and point out to you that when you are limited to 1 mole of the substance, that will sometimes mean that you have fractional coefficients. And I'll show you what that looks like. So under normal circumstances, when we taught you to balance equations, we said you had to have whole number ratios. But for these special enthalpies, you can have fractional coefficients, and delta H of combustion is one example of that. The second is the delta H of formation. Delta H sub F means the delta H of formation. And this is the enthalpy change for a reaction in which exactly 1 mole of a substance is formed. It's a pure substance formed from free elements in their most stable standard states. So those are standard states under the standard state conditions of which we said before, were 298 Kelvin, which is 25 degrees Celsius, and 1 atmosphere pressure. So under delta H, that's the delta H zero. So you will see these in tables, and they will be listed as delta H 0 sub F, comma 298. And you can see here an example. This is the formation of ozone. And you can see that to form ozone, we have to use oxygen in its standard state, which is O2. So to form 1 mole of ozone, we need 3/2 of a mole of oxygen. So you'll get these from tables. I'll go back and we'll do those practices in a minute, but you can see on the left, you'll see the standard molar enthalpies of combustion. And you can see they're not all organic compounds. The bottom ones are all organic compounds, but you can have the hydrogen plus oxygen formation of water. That's considered a combustion reaction. As I said before, magnesium plus oxygen forming magnesium oxide, sulfur plus oxygen forming SO2, et cetera. So those are the examples of combustion reactions. And the number that you're given is in kilojoules per mole of that substance, whatever it is. And on the right, you see standard, a piece of a table for some thermodynamic data. We'll get to delta G next semester. You're not going to worry about that now, but the delta H of formation, those are the, according to the equation, the formation of 1 mole of that substance from its constituent elements in their standard states. Notice that the delta H of formation for an element in its standard state is 0, because that's your reference point. So aluminum here, solid, is its standard state. So the delta H of formation is 0. If you want to talk about the gaseous form of aluminum, that is an endothermic reaction, which should make sense in order to vaporize aluminum metal. That's going to take energy. It's going to take an input of energy, and that's a positive delta H of formation. Same thing is true for antimony. So anytime you see an element in its standard state, the delta H sub F is 0. You can tell from tables, and I have, your book doesn't have a really good one, but I have a table here that I pulled up that's a little bit more extensive than the one on the slide. You can tell what the standard state is by where the 0 is. So iodine, I2 solid, that's its standard state. The one thing I will call your attention to, I hope it's here, I looked for it, but is carbon. I see CCl2. I guess I'm sorry, I guess carbon is not here. Carbon has 2 solid forms. So sometimes under normal circumstances, just saying carbon solid is not enough. You have carbon as graphite and you have carbon as diamond. The standard state would be carbon as graphite, not as diamond. So let's go back to our PowerPoint. Whoops, I'm sorry. Let's see. Cancel that. I need to go back to where we were. Okay. So let's take a look at some of the types of things that what you should be able to do. What I would like you to be able to do is look at a sentence that says, if you're talking about the combustion of a substance, I would like you to be able to picture in your mind what that combustion equation would look like, and then you can balance it. So if you're talking about enthalpy again, it's the enthalpy of 1 mole. So the combustion equation, and this is diethyl ether. Diethyl ether, what you're talking about then is C2H5. These are written the way an organic chemist would write it, which is supposed to give you a hint on how those substances are linked together. Notice that you have a chain C2H5 on either side of an oxygen. So enthalpy of combustion would be plus O2. This is liquid. States matter. That's gas. And it's going to form CO2 plus H2O. And then this has to be a 1 because it's the enthalpy of combustion, so it's per mole. So we have to balance it. We have 4 carbons on this side, so we need to put a 4 over here. We have 5 and, oops, I'm sorry.
What happened to the H5?
That's the H5. That's an H in there. I'm sorry. I put a 5, but I didn't put the H. C2H5. So there's 10 hydrogens. So we have 5 waters on this side. And now we count the oxygens. We have 5 plus 8. Okay. So let's see. We have one odd one can come from the diethyl ether. So we have 8 plus 5 is 13. So we have 12 O2 or 6 O2. We need 12 oxygens from the O2. So there's your 6 O2. Write the enthalpy of formation equation for C2H6. Okay, this is carbon as graphite plus hydrogen gas, H2 gas is its standard state, forming C2H6. And it must be 1 mole of C2H6. So we have to balance it on this side, on the left side of the equation. We need 3 H2s and we need 2 carbon graphite. Okay, so it's 1 mole, the formation of 1 mole of C2H6. I'm going to let you do the other 2. This was the top one was the enthalpy of combustion. The bottom one is the enthalpy of formation of diethyl ether, which is a different reaction. You should be able to write those. Okay. So what we're doing in this chapter is we're learning how to calculate enthalpy changes. You learned one way of calculating enthalpy changes in a constant pressure calorimeter. The heat flow is a measure of the enthalpy change of the reaction or the process that is going on in that calorimeter. So Q equals mass times C times delta T. That's one way of calculating enthalpy changes. There are other ways of calculating enthalpy changes as well. One of those is known as Hess's law. You can determine the enthalpy change for a reaction either by doing an experiment and measuring the heat flow if it's under constant pressure, or you can use similar reactions. Hess's law states that the enthalpy change going from a particular set of reactants to a particular set of products is the same, regardless of whether that reaction occurs in one step or multiple steps. That's because enthalpy is a state function. The steps that occur to get from those reactants to that product or those products is the same regardless of the pathway used to get there. So it doesn't matter if the reaction occurs in one step or it occurs in 2 steps. In your last lab, you did a reaction that occurred in 2 steps. There was a displacement reaction and then a decomposition reaction. You could not physically separate those 2 reactions in the vessel in which you did them, but technically it was a two-step reaction. So reactions can occur in multiple steps. So if you want to measure the enthalpy change, the combustion of carbon to form CO2, you could do that reaction directly, or you could measure the enthalpy change for the combustion of carbon to form carbon monoxide first, and then a second step combining carbon monoxide with another oxygen atom to form CO2 and add those two. So whether this reaction occurs in one step or two steps, the reaction, the overall enthalpy change is the same. You can see that on the diagram on the right, where you start with the reactants carbon and oxygen. You can either do it in two steps, going to carbon monoxide and then carbon dioxide, or you can do it in one step, going directly to carbon dioxide. The enthalpy change is the same regardless. That's known as Hess's law. That means that if you can find two or more reactions that you can manipulate in a way to combine them to add up to your reaction of interest, you can use the enthalpies of those reactions to calculate. I'm going to do an example of that. We're going to calculate the enthalpy change for the process of nitrogen gas plus oxygen forming NO2. And whoops, sorry, very sensitive mouse. We're going to use these two reactions as given in order to do that. So let me switch my camera. So there is the reaction that we want. We want to calculate the enthalpy change for. And we were given two reactions. So we were given N2 gas plus O2 gas forming 2NO gas. And the delta H for that reaction was equal to 180.5 kilojoules. The second reaction we were given was NO gas plus 1/2 O2 gas forming NO2. And the delta H for that reaction was equal to minus 57.06 kilojoules. Okay, well, you have to move my camera, sorry, just a minute. There you go. Okay, so we have to see if we can find a way to do this. I'm going to tell you that we want to somehow add these two equations together in such a way that we end up with this as our overall reaction. We want NO2 as our product. In this reaction, it is the product, but notice we want 2 NO2 and we only have one here. We also have NO as a product here and NO as a reactant here. NO isn't in our final equation, but notice that they're on opposite sides of our arrows. Remember, we can think of our arrows as an equal sign. We can cancel on opposite sides. We can cancel like species. So if we multiply this reaction times 2, we'll get 2NO, and that can cancel, and we'll get 2NO2. So let's do that and add those together. Remember that if we multiply this reaction by 2, we also have to multiply delta H by 2. So we end up with N2 plus O2 gas from our first reaction plus 2NO gas plus O2 gas from our second reaction, going to 2NO gas plus 2N2, excuse me, NO2 gas. And like species can cancel. So those two are the same on both sides. We can add these two oxygens together. So we have N2 gas plus 2O2 gas forming 2NO2 gas. And that's exactly what we wanted. So how do we figure out the delta H?
Okay.
Yes.
I think you canceled the wrong thing for the product.
Oh, I did
side.
cancel. I'm sorry. I did cancel the wrong thing. My bad. I'll put this back. 2NO2. Okay. How to get the delta H for this reaction was used as is, so that's 180.5 kilojoules. And we have to add together this one, minus 57 times 2 is a minus 115.1 kilojoules. We add those two together, just like we added these two equations. We add the enthalpies together, and the enthalpy for that reaction is 66.4 kilojoules for the reaction N2 gas combining with oxygen to form NO2. Okay. You can sometimes see problems that require you can see them with requiring 2, 3, 4 reactions. They sometimes get a bit more complicated when you have more reactions that you have to work with. But I always like to look for the product and try to figure out what reaction gives me that product and write that. You can also be asked to reverse an equation. If you have to reverse an equation in order to get where you want to go, remember that the sign of delta H reverses as well. The number stays the same, but the sign reverses. So you could be given problems where you have to reverse delta H.
Do you have an example of one of those problems?
I don't today, but I can certainly get one. And we have class on Thursday. I'll be happy to share one with you then. I can share you the one I gave on my final last year. How's that?
Okay, cool. Thank you.
Seems.
Sorry if you said this already, but what are we doing on Thursday?
I'm going to be giving you a little more information about your final. I'm still working on it. I'll give you a little bit more information about your final, the material that's covered. Obviously, you know, chapter 8 and chapter 9, but I'll give you more information about the other stuff that you'll have to do and how many questions it's going to be. I'll just be available to answer any questions you have, but it's really just to more of a review session.
Okay, cool.
Okay, so let's see this one. Okay, so that was that first one. Second question here, which produces more heat? This is a combustion of osmium. And the first one, you have a combustion of osmium forming solid osmium oxide, and the second one, it's forming gaseous product. Which of those do you think produces more heat? In other words, which one has the greater delta H?
Gas one?
Greater negative delta H.
The gas one?
Say which?
The one with the gas?
And what's your reasoning?
It just came to me.
Okay, chemistry, nothing can just come to you. You have to have a reason for it. Okay, so note it says that there's a phase change going from OSO4 solid to osmium oxide gas. that means this plus means that it takes energy. There's an input of energy to convert the solid to the gas. And that makes sense. It takes energy to vaporize something. So you're having to put more energy in to form that gaseous product. That means that forming the solid product is going to be have a greater negative value. It's going to produce more heat than producing the gas, because when you have to produce the gas, you have to absorb energy to do that. Okay.
I'm sorry, but can you explain it again?
Sure. In order to go from this state to this state, you have to put energy in. If you think about the reaction producing heat, in order to produce the solid, you can produce more usable heat. To produce the gas, you have the overall reaction produces less usable heat because this amount of energy has gone into vaporizing the osmium tetroxide. So some of your heat, the heat from the reaction, is used to vaporize the product. So the reaction produces less heat that's usable. Does that help?
Oh, okay. Yeah, that makes sense. Thank you.
Okay.
Which one produces more heat?
So the one that produces more heat is the first one. The one producing the solid product. Okay, so I've
Professor,
labeled
sorry.
this. Yes?
So if it changed state from like gaseous form to liquid, would that be less heat?
If you, from which point? I mean, are you talking about comparing it to the solid product or the gaseous product? I'm not sure what you're asking.
Let's say we have like from gas to liquid, would that be less heat? Just asking.
If you have a gas that is condensing, that process is exothermic.
Okay.
Condensing of a gas is exothermic. So that would produce heat going from a gas to a liquid. Okay, another way to use Hess's law is to use enthalpy from the heats of formation. So using a table where you get those delta H of formation numbers. And all we're saying here is that the heat of a reaction can be calculated by summing N is the number of moles present in the equation times the delta H of the products minus the sum of the number of moles of reactants times the delta H of formation of the reactants. Remember, N is moles. And if we multiply that times kilojoules per mole, we end up with kilojoules, which is our energy measure. So what we're saying is that if you used enthalpy of formation equations in place of the species in the reaction, you could sum the enthalpy of formation equations together and you could end up generating an overall equation. So it's a form of Hess's law, but instead of using the equations to calculate the delta H, you can go directly to tables that will give you the delta H of formation. So you can basically what we're saying is that whatever energy is in the products minus the energy that's represented for the reactions will sum to delta H of reaction. So I'm going to do this particular problem for you. We're going to calculate the delta H of reaction for this particular reaction using the enthalpies of formation. I will tell you that you will either be given, your book doesn't have a really good table. The appendices that I think you were given does not have a really good table. It may have a table in the text itself, but it doesn't have a table in the appendix that is a good one. So chances are, if you're asked to do a problem like this, you'll be given something that looks like this. This indicates all of the species that are in this equation, and these are the enthalpies of formation that you have to use. So we would say that, let's say that the delta H of reaction is equal to the sum of the number of moles of the products times the delta H of formation of the products minus the sum of the number of moles of the reactants times delta H of formation of the reactants. That's the overall equation that you have to use. Remember, it's always products minus reactants. So we can start plugging numbers into this. We can say that this equals the number of moles of NO is 4. So it's 4 times the delta H of formation of NO gas plus 6 times the delta H of formation of water. And in this case, water is a gas. Delta H of formation of water as a liquid is different than delta H of formation of a gas. If you're working off of a large table, you have to make sure you take the right one. In this case, I've given you just the one for the gas. And we subtract from that 4 times delta H of ammonia plus 5 times delta H of oxygen. And now we can just start plugging in numbers. So 4 times 91.3. I'm not using units here. I'll use partial units. Understand that this means 4 moles times 91.3 kilojoules per mole. So the moles cancel. So 4 times 91.3 kilojoules plus 6 times negative 241.8 kilojoules. That's the reactant side, the product side rather. And we subtract from that the reactant side, which is 4 times minus 45.9 kilojoules plus 5 times 0.0 kilojoules. That's the reactant side. This simplifies to a minus 1085.6 kilojoules minus a negative 183.6 kilojoules, which simplifies to minus 902 kilojoules. So the heat of reaction for this overall reaction is a negative 902 kilojoules. Is that endothermic or exothermic?
Exo.
Exothermic, exactly. Okay. Let's go back here. Okay, so that's how you do. You could also, I will point out to you, you could also be given delta H of reaction. So you might be, in a case like this, you might be asked to calculate the delta H of formation of one of your products. Maybe you'd be asked to calculate the delta H of formation for NO2, for example. If that was the case, you'd be given the delta H of reaction. You use the exact same formula, except that you are given the delta H of formation of the reaction as a whole. You would be given a table that gives you the standard enthalpies of formation of water and ammonia. You know that oxygen is in its standard state, so delta H of formation is 0. And the only number missing then would be the heat of formation of NO. So you could be asked to calculate that as well from a similar type of reaction. Okay, so bond energy is another way of calculating heat of reaction or enthalpy changes. Bond strength describes how strongly each atom is joined to another atom and therefore how much energy is required to break that bond. It always requires energy to break a bond. You always have to put in energy in order to separate two atoms. That means that to put in energy is always an endothermic process. It always takes energy to break a bond. When a bond forms, you always release energy. So forming a bond is always exothermic. Breaking a bond is always endothermic. Overall reactions are either exothermic or endothermic, depending upon whether the breaking the bonds in the reactants requires more energy than you get back in forming the new bonds in the products. That determines whether the overall reaction is endothermic or exothermic. But it always is endothermic to break a bond and exothermic to form a bond. So we call that the bond energy. D is given as the symbol for the bond energy in a covalent molecule. So here's an example of what we're talking about. These, you'll see tables that give you bond energies for certain types of bonds. These are all single bonds. The bond energies for double bonds and triple bonds are obviously different. So a carbon-carbon single bond is going to take less energy to break than a carbon-carbon double bond, which takes less energy than breaking a carbon-carbon triple bond. We talked about relative bond strengths and bond energies back when we were doing our unit on molecular structure. So the change in, for molecules with multiple bonds, you have to sum the energies for breaking all of those bonds. So to take a methane molecule and break it up into its constituent elements, carbon and 4 hydrogen atoms, would take 1,660 kilojoules because it would be the sum of all 4 of those bonds. And there is a table of bond energies in your book. To calculate delta H, the enthalpy change for a reaction is approximately equal to the energy required to break all the bonds in the reactants and the energy released from the formation of all the bonds in the products. Bond energies are listed in tables and they're always listed as positive numbers. They're always listed as positive numbers. Remember that that bond energy is positive if you're breaking it, but negative if you're forming it. The tables will always list it as a positive number. That means that unlike what we just did with delta H of formation, in order to calculate delta H here, it is the summation of the bond energies for the bonds broken minus the sum of the bond energies of the bonds formed. Bonds broken means reactants, and bonds formed means products. So for delta H of formation, it was products minus reactants. For bond energies, it's bonds broken, reactants minus bonds formed. And that's because the numbers you're given are listed as positive numbers. And when you're forming bonds, it's a negative number. So we have to subtract the bonds formed. So we can look at this reaction, methane. This is a combustion reaction for methane. All we're doing is we're saying, okay, we can break all the bonds in the reactants. We can break those 4 carbon hydrogen bonds. We can break the 2 oxygen double bonds, and then we can form new bonds in the products. We can calculate all the energy it takes to break all of these bonds. We can calculate all of the energy that is released when we form all those new bonds. And the first number minus the second number gives us the delta H for that reaction. Okay, so we can use bond energies as another way of calculating delta H. I'm going to let you do this, and you'll notice I tried clicking on that table and it was a broken link for me, but you can certainly look up tables of bond enthalpies. I think you have one in your book. I will tell you that the easiest way to do this, I'm going to give you a hint on this. The easiest way to do this is to draw your Lewis structure. Because your Lewis structure is going to tell you if you have a double bond somewhere. It's going to tell you if your bonds are single or double or triple bonds. So draw your Lewis structure. You can also then look, and it's easy to forget breaking a bond if you don't have the Lewis structure. One of the common ones is to forget the breaking the bond in a diatomic molecule like hydrogen or fluorine. But if you draw the Lewis structure and recognize how many of each of those types of bonds you have to break and how many you have to form, you can calculate delta H. I will post answers to this and you can certainly practice that. This is just a brief discussion on ionic bond strength and lattice energy. Ionic bond strength is really based on the strength of your ionic charges and the distance between them. So the lattice energy for an ionic compounds is composed of the charges on the ions, Z1, Z2, the interionic distance, that's R, and a constant that depends upon the type of crystal structure. And so you need to know what type of crystal structure the system has. So this is an example of how this is used, very similar to what we did before with Hess's law. We can break this down into separate reactions. This would be the formation of, or the lattice energy for cesium fluoride. Up arrows and down arrows indicate whether it's a endothermic or exothermic. So let's take a look at this. We can say that if we want to take cesium as a solid plus 1/2 fluorine gas, and from that form cesium fluoride. The lattice energy is the last step. So let's see what we have to do. The first thing that we have to do is we have to vaporize our solid. We have to take our cesium solid and turn it into cesium gas. So we can measure the energy that it takes to break the attraction between cesium atoms. That's an endothermic process. We also need to ionize that cesium. So we have to take that cesium metal and turn it into, and that's the ionization energy. That's IE. Okay, so we have to ionize the cesium. We also have to break the bond between fluorine. So we have to go from an F2 molecule to an F atom. Okay, that's 1/2 the bond enthalpy. And that takes us from here to here. Okay. It takes, what we're doing is the bond enthalpy is breaking that fluorine molecule into 2 atoms. We take half of that because we're only going to use 1/2 of that molecule. So all of these are endothermic processes. We also have to add an electron to that fluorine atom. That's electron affinity. And that is an exothermic process. So we can find that from a table. That takes us to our cesium ion and our fluoride ion. The difference, or the rest of the energy, is the lattice energy. So delta H of lattice energy takes us back to cesium fluoride. Lattice energy is defined as the energy released when 2 isolated ions come together. And so we can do this in what we call a Born-Haber cycle, which is essentially Hess's law in action. We can measure each of those steps. We know that the overall enthalpy for this reaction is a -553. So we know the left side, and so we can calculate the lattice energy because we can calculate every other piece of this reaction, and mathematically the 2 sides have to equal each other. Okay, so I've given you some practice problems here, which you can certainly try. I have a feeling most of you will probably not care about that when I tell you that that is only going to be on the test as extra credit. You're not going to be asked to do that for the test. There'll be an extra credit problem on lattice energy, or there'll also be, if there's a question at all on bond enthalpies, that will be done as an extra credit. The only thing I will be asking you to do is up through Hess's law for the test.
What do you mean for the test? What test?
For
The
for the
exam?
final exam.
Oh, okay.
For the final exam. Okay.
Thank you.
Bond enthalpies, it's those of you that have intentions of going on to second semester, some of this stuff will come up again in second semester. So you might want to at least go through and try to do those practice problems that are up on the PowerPoint. Thermochemistry comes back again, and it comes back not right away, not when we first start second semester, but I think it might be the 2nd or 3rd chapter. I think it's the 3rd chapter we do when we come back in second semester. So we're going to expand on our concepts of thermochemistry. We're doing delta H now, but we're going to talk about entropy, and we're going to talk about free energy in the second semester. And those are expanding on our concepts of energy changes. So having a more solid understanding of delta H will help you in the second semester. So if you're planning on going on to take second semester, I would suggest you may at least try those practice problems. There were no assignments in your text, or there were no assignments in Newton on that last part of the chapter. If you want to look at them, there are questions at the end of the chapter in your text, and you can work on those. And I'm happy to help you with any of them if you have questions on them. Any questions from anyone on the material we covered today? I think I sensed a big sigh of relief when I said you don't have to worry about bond energy. You don't have to worry about the Born-Haber cycle. Yes, Chow is applauding. I know that most of you are at least inwardly applauding. yes. But they, you will have to know up through Hess's law. So if there are no questions, by all means, go take your quiz. It's a quick one.